who is giving a presentation in person. And he's also actually the first collaborator for our center and KAUST, started in 2009. So Professor Bruce Logan, he's an even few professor in engineering, the Stan and Flora Kappa Professor of Environmental Engineering, and the Director of Engineering Energy and Environmental Institute at Penn State University. He is well known for pioneering the field of microbial electrochemical technology and microbial electrochemical systems, microbial fuel cells, microbial electrolysis cells, microbial desalination cells. He has more than 582 refereed articles, more than 100,000 citations. His H index is 154. In 2019, it was 139, so around 8 per year. His current research efforts are in renewable energy production and the development of an energy sustainable water infrastructure. He is a member of the US National Academy of Engineering and the Chinese Academy of Engineering, and a fellow of the American Association for Advancement of Science, International Water Association, Water Environment Federation, and the Association of Environmental Engineering and Science Professors. So please join me in welcoming Professor Bruce Logan.
Thank you very much for that. It is, as always, a pleasure to be back here. I really, it's been a long time, and as I measure visits to KAUST, I usually get back here once a year, and obviously that hasn't happened in the past couple of years. So today I'm going to talk about a whole overarching view on hydrogen, touching upon our water infrastructure and our climate challenges. And so it'll be fast, maybe furious, I don't know, but we'll start slow. And the slow part is a little bit out of the past. When KAUST was originally envisioned, this was how it was envisioned in terms of these institutes. This one up here, Institute for Resources, Energy and Environment, things like carbon sequestration and hydrogen and fuel cells. Pretty interesting to think about how relevant that is today from the time at which KAUST was sort of imagined. And maybe we need to come, I would implore you maybe to reconsider the WDRC as rethinking about how much you might expand in some of these directions as well. I think hydrogen is a really nice center point, focal point for several different centers as they exist here today, particularly water, particularly catalysis, membranes, and certainly process engineering. In environmental engineering, we like to think that we really do have a broader title, right? Environment engineering. But in fact, a lot of it's water engineering or pollutant engineering. And I think we need to look to this vision of environmental engineering for the 21st century and really look at what that says. It's talking about our infrastructure. It's talking about how we look at the interface between energy, water, climate, and environment. You know, and civil and environmental engineers are, sure, we're involved somewhat in the food infrastructure, mainly in the water infrastructure, but that's 13% of US energy going into our water infrastructure. Another 13% of our CO2 emissions are in concrete, or globally are in concrete and steel. And of course, then you have emissions from transportation. And as we go to electrification of our infrastructure, a lot of it currently exists from fossil fuels, and our goal is to move away from that. But how far can we move away without also building in carbon sequestration? You know, this is the path we're on. We know where the future is going. It's going to 4 or 5 degrees C above levels that existed sort of back in pre-industrial times. And the only dip we've ever seen here is actually right here with COVID. But you know, the historical recovery is that anything that interrupts the sort of global CO2 emissions, like the one here in COVID, but like others, quickly resumes back onto the line because that's where people want to be. So we have to think about where the future is going and how we're going to stop this upward trend of CO2 emission. And we can't do the whole thing, but what part can we do? What system can we address? And I would argue that maybe hydrogen and water have a unique nexus within a part of this, certainly not the whole thing. And so I want to talk today about hydrogen, why it's important, what are the challenges, how do we make it, and what activities are going on in the world relative to green hydrogen. Now, 20, 30 years ago, people were talking about the hydrogen economy and hydrogen for transportation of cars. But I think if you look now at the plans, electric vehicles have taken over for automobiles. And the real action here is what are we going to do about these heavy duty vehicles, trucks, trains, planes, international shipping and things like that. And that's where hydrogen starts to come in. Because if you look at the energy density of petroleum or gasoline, it's about 12 kilowatts per kilogram, or about 50 to 100 times greater than a battery. And hydrogen, maybe about 10 times. Gasoline, about 10 times hydrogen. So hydrogen can fill this area where things just become too heavy if you try and do them with a battery, and that's not likely to change. An airplane can be up to 50% of the weight at takeoff is due to that fuel. So you can't replace that with a battery that weighs 100 more times. The plane does not take off. So that's why we're seeing this renewed interest in hydrogen. We see it happening in Europe and the Netherlands and Spain and Germany, also in the US. We see investments in carbon-free ammonia, carbon-free hydrogen, and indeed, if we're going to have something that's transportable as a fuel, hydrogen probably could lead the way. And we don't have to look very much further than Saudi Arabia to see big plans, one of the biggest plans in the world, a $5 billion hydrogen plant to make hydrogen, convert it into ammonia, ship it somewhere, and convert it back to hydrogen. Maybe. There's many different aspects of where hydrogen will be used in terms of chemical production. Even refineries make a significant and consume a significant amount of hydrogen just in the production of gasoline and other fuels today. So this is widespread, and everybody expects this to grow, from 100 metric tons to maybe 500 in the coming decades. Now in the US, they've recently started what's called the hydrogen shot. It's on the idea of an Earth shot. It's called the 1-1-1 plan. $1 for 1 kilogram of hydrogen to be achieved in 1 decade. I personally don't think they're going to make it. And I can explain why, but it's a nice goal. It's something to work forward to, and I think that's really the issue. And so they've come up with 3 different sources: fossil sources, biomass sources, and water splitting. So these are the different colors of hydrogen, depending on where you get it from and what the emissions are. So brown would be something like starting with coal. Blue would be natural gas if you perform carbon sequestration. And then over here you have green, which would be water electrolyzers from renewable energy as a part of this. And the question is, when everything is currently made here with what we'll call gray hydrogen, which is natural gas with no carbon sequestration, that's where we are primarily now. How do we get to this one, or how do these other ones fit into the mix? People say that carbon sequestration is a critical role to the use of any of these fuels to make hydrogen. Unfortunately, one of the main uses of putting carbon dioxide back into the ground is to use it to eject more petroleum. That doesn't seem to be a very climate change oriented good direction. So if you look at this, let's see where we really can get to if we want to get to have really green hydrogen. Well, I don't think nuclear is going to work. It's just too expensive. I don't think we want to use coal. The carbon emissions from coal are just terrible. We don't want to use natural gas without sequestering the carbon. And that leaves us basically with trying to look at natural gas with carbon sequestration, either in the form of solid carbon or carbon that we inject under the ground. So some way to hang on to that carbon. But I would actually say that that is not feasible for other reasons, not because even if putting it in the ground is feasible, there are other reasons not to do it. And let me explain why. So when we take a gram of methane, say natural gas, if we were to release it as CO2, it would have, by conventional thinking, about 20 times the greenhouse gas impact or CO2 equivalent of carbon dioxide. If we combust that methane, 100% combustion, complete it completely to CO2, well, 1 gram of methane is going to release 2.7 grams of CO2. But that's not quite the full picture. When we take that natural gas out of the ground during production, transport, extraction, and use, we leak some of that methane into the atmosphere. EPA says it's about 1.4%. And if you use a greenhouse gas equivalent of 21, that CO2 addition adds about 11% of just the CO2 that was released during combustion. But the problem is that the methane that's released isn't around for 100 years. It's around for about 10 to 20 years. And so its impact over the time it's around is actually much greater. And if you look at a 20-year scenario, its impact is about 80 times that of CO2. Now that's good because once it gets up there, it goes away faster. But the problem is unless you slow it down, it's having an 80-fold impact compared to that CO2 emission. So what that means is if we're leaking 2.3%, and this is out of a study by Alvarez et al., that's looking at about 71% extra CO2 equivalent release into the atmosphere due to that methane. So if we're turning methane into hydrogen, and we're leaking just this amount, even if we capture everything over here and put it in the ground, we have almost an equivalent amount of methane that's leaked up into the atmosphere. So unless we control that, there's no point in using natural gas to make hydrogen. You're just going to release as much CO2 as you would any other way. The impact of this 85 number is really important, and environmental engineers do a lot of anaerobic digestion, and we do biomethane. And whether it's biomethane or fossil methane, once it's in the atmosphere, it has the exact same impact with like a one difference. Biomethane's like 84, and fossil fuel methane's 85, because the biomethane came out of the atmosphere to begin with, presumably. But this impacts the greenhouse gas emissions by the US go up 25% if we use this 85 scenario instead of this 21 scenario. So this is a really important view in terms of how we look at the future, what fuels we can use, the role of natural gas, and the role of environmental engineers also in things that we do in anaerobic technologies. We've also, by burying things in landfills, created a relatively large source. This is about 15 to 20% of this. Here's the natural gas-based systems. And then enteric fermentation, well, those are cows and other animals. So these are things that we need to really focus on to control methane emissions. And even if we don't do natural gas systems, we're going to have to contend with these other issues. So how are we going to make this hydrogen using water electrolyzers or maybe biomass if we're not going to use these fossil fuel sources? Very quickly, a water electrolyzer, there's 3 approaches. One's a high temperature, I won't talk about that. So the 2 not high temperature are acidic and alkaline, or a PEM-based system where you ideally split the water over here, protons flow and are turned into hydrogen. Here it's under alkaline conditions, and so I'm not going to go into this one as much, but the same general principles apply. So some people have said, well, you know, can we run these water electrolyzers without really ultra pure water? Because you have to have RO water and water that goes through capacitive deionization, so very, very like minuscule conductivity. And so people have talked about using seawater. And there are reasons to use seawater or impaired water, brackish water, which are partly due to economics, but also partly due to convenience and system control and performance. So if you try and use seawater or anything with chloride ions in it, the chlorine reaction occurs more readily than that of oxygen because this is a 2-electron transfer rather than a 4-electron transfer. And so you just end up making chlorine gas. And that's, of course, toxic. It's also aggressive and will degrade the membrane and the other components in the system. So we looked at ways we might be able to use seawater and not have to worry about chloride transport onto the anode. So it's really over here, right at the anode. This is where the cathode is where the hydrogen's being evolved. The anode is where the water is being split or the chloride is being converted to chlorine. So we thought, you know, those PEM membranes, they're kind of expensive. Can we use an RO membrane for this same purpose? RO membranes, because we make them by the thousands of miles per year, you know, instead of ion exchange membranes, which we make very little of. So mass production has really reduced the cost of these RO membranes. And they're about, you know, 1/10 of the price of ion exchange membranes. And so this is some work done by somebody who graduated from KAUST, Lushi, who is working in my lab now. And she worked on this. And the concept here is that we want to have a contained analyte which doesn't have chloride ions, maybe something like perchlorate, which is the most highly oxidized form of chlorine. And then we can use seawater here. And if we keep this flow at a reasonable amount, we won't get, hopefully don't get deposition on that electrode. Now, I don't think I have to explain RO membranes to this crowd, but just a quick refresher. The focus here is on the fact that there's an active layer, which is very effective at screening out big ions like sodium and chloride, but actually not so good at screening out ions like protons and hydroxyl ions. And so hydroxyl ions and protons can pass these membranes far more readily than these salts. And what that sets up the ability to do is to contain the salty solution over here from here if we have an RO membrane, because it's rejecting those ions. Whereas if we tried to use a CEM or an AEM in a typical system, that AEM would pass chloride ions and the CEM would pass sodium ions. So you wouldn't get the charge transfer of the sodium that you would need to go to the cathode. So for both chlorine evolution and as well as ion balances, the PEM doesn't work very well for seawater. So here we say, well, we'll keep the chloride out of here. Of course, there will be some leakage of chloride here. We're producing protons. They move through the RO membrane and then function it the same way. But we have a contained salt solution here, and this water then provides the electrolyte, but also because the RO membrane is permeable to water molecules either through pressure or forward osmotic potential differences, we could draw water into there in that way, keeping this at a higher salt concentration. So what did we find by testing out this idea? Well, the intrinsic property of the membrane, an RO membrane, is that it has to have, quote, low resistance. It has to be really permeable to these ions in a way that might compete with these. This is a selenion, naphion. These are two cation exchange membranes. You can see their resistance is very low in these salt solutions. You see these other two. This is a brackish water RO membrane, either facing the cathode or facing the anode. There's not much difference. And this is another membrane. You see this one has very high resistance, would not be suitable. This one has much lower resistance, at least intrinsically in a conventional test here, where we don't get a lot of proton gradient building up across the membrane. You can look at how the current density can be sustained by applying a voltage. That is, can I apply the least amount of voltage and get the highest current density? That's the lowest energy use. And this is doing a sweep of voltage. And this one is setting different current densities and seeing what the voltage is that is needed to maintain that current density. If you look here at the highest one, 40 milliamps per centimeter squared, you can see these two lines are very close. One line is the Nafion, that's the gray line, and then the line right next to it is this red dashed one, and that's our brackish water with the membrane, the active layer facing the cathode. So what this tells us is that we get about the same amount of necessary voltage to achieve the same current as Nafion using this membrane. So that's very encouraging. We also looked at current densities across these systems, and this really doesn't work too well because what it says is that the electrode resistance is kind of the catalyst that we're using starts to dominate the system. So it's saying, look, the membrane isn't that important from that perspective. It's really the catalyst that you're using. So to really increase the current densities, we would need better functioning systems and catalysts. We also looked at gas recovery, and we're up here really at 100% of hydrogen recovery. We also looked at leakage of ions. Now, no membrane, no RO membrane is perfectly selective. It doesn't reject perfectly all salt ions. If it did reject it perfectly, it would mean there would be no water flux, but of course, such a membrane wouldn't be very useful for desalination. So we looked at how much sodium would be coming across, or potassium or chloride or perchlorate leaking across these membranes in the direction of the electric field. You can see that anions go to the anode, cations go to the cathode. And so, you're going to get sodium going to the cathode. You're going to get chloride going to the anode. That's the direct enhanced field effect on those ions. Whereas the perchlorate going against the electric field, or potassium going against the field, is lower. And that's basically what we found for the RO membrane, but with the PEM, it always favored cation transport because it's a cation exchange membrane. So there is some leakage of ions. It's not perfect. The question is, how much of the charge that is going through the circuit, the current that's going through the circuit, is due to those ions? And if you look at the fraction of the charge carried by the proton, you can see that just look at 40 milliamps per centimeter squared. This is 1 down at 10. And you can see that this SW membrane and BW membrane are transferring a lot more of the charge by the proton flux. And so that means some of the ions that are leaking across this membrane are helping to sustain the current, but the proton transfer is also doing a large part of that. Yeah, this is just looking at whether the amount of ions leaking across this membrane is changing over time. We would hope all these would be flat lines. They're slightly increased. We don't really know why it goes up. That could suggest some membrane damage, or it could be just wear and tear on the membrane. We don't know. But you'd want to have these systems to be completely stable in terms of ion leakage over time. And it looked like it was increasing slightly. We don't know the reason for why that occurred. So there are many other things to be done before we go out and start building massive water electrolyzers with these systems. And that gets us back to, again, what are the catalysts? You need a catalyst which is stable in very acidic solutions. Excuse me. And those are still being developed. Right now we use iridium. Iridium oxide is really a very precious metal, and so we don't want to have to use that, and we use platinum at the cathode. But with this system, we could use other catalysts at the cathode, because this is going to be more alkaline, and there are non-precious metals you can use for the alkaline part. But the acidic part, we're still is going to be a challenge. PEM systems work better than, or acidic systems work better than alkaline systems because the PEM is very good at letting pressure build up there. So you can have a pressurized hydrogen gas coming off of the water electrolyzer in a PEM system, but in an alkaline system, if it's got a separator, which is not really ion selective, then you can't build up the pressure. And so you lose a lot of the value of that because you have to pressurize hydrogen from 1 atmosphere or 2 atmospheres up to 700, which takes quite a lot of energy. But if you can get it up to 30 or 40 in just the electrolyzer itself, you save a lot of energy. And you can do that with an RO membrane and a PEM membrane. We also envision that the water that's being transported into the anode chamber to replace that being electrolyzed. In the case of a current being 100 milliamps per centimeter squared, that's about 0.34 or about 0.3 LMH. That's certainly within the range of what these FO and RO membranes could accomplish. I won't go into it today because it's work we haven't published yet, but we're also working on a system that uses the same CEM, but its architecture and operation is a little bit different. And without giving too much away, because I'll have to come back and tell you about that next time or something, but without giving too much away, our system here, if we just use DI water, it would perform as well as a conventional PEM acidic system. If we have impaired water with just a little bit, this would be like a 10th, this would be about a 10th of seawater. Even if it's got some ions in it, it actually will work about the same as this system. And it works, it doesn't work quite as well because of, without going into too many details, because of how the ion exchange membrane holds things other than protons. It holds sodium, and that decreases its efficiency of ion transport. But this could be more successful because we don't have to fully go through capacitive deionization to these ultra pure water systems. We could just regular RO water would be way sufficient for this case, and even more impaired than that. It could even be just groundwater. So this is something that we've submitted, and it's under second review, so I hope that'll be out soon. So that's the water electrolyzer part. The third part of this is using biomass as a way to make the hydrogen. I've been working in this area for many years now, originally starting this with Pincheng Manes, who's now an emeritus researcher with National Renewable Energy Lab, and we recently participated in one of these ersatz, excuse me, to discuss the, trying to get to this 1-1-1 goal, $1, 1 kilogram, 1 decade. And so you can ferment cellulose. In the US, there's enough waste biomass. They call it the billion-ton supply of waste biomass that could be available to convert to hydrogen. And many years ago, I calculated that if we had done that and started doing that back in a little after 2000, that we could have essentially fueled all the cars on the road by 2050, 2060. Now that never happened, and it doesn't look like it's going to happen with light duty vehicles now. But the real problem of doing 12 moles of hydrogen per mole of hexose equivalent is that you can ferment only to get 4 moles of hydrogen, and you end up with 2-acetate under the very best conditions. And so we have explored using a microbial electrolysis cell where you can add in a little extra energy and therefore drive the system more to completion. We can get up to almost 8, and so we've gotten as high as 10 or 11 moles of hydrogen per mole of hexose. Now, before I tell you about the advances we've made in MECs, I want to talk about MFCs, microbial fuel cells, because we've done, if we've done that much work in microbial fuel cells, we've done about that much work in microbial electrolysis cells. And so I want to say, what did we learn from all the microbial fuel cell stuff that's going to help us to do this microbial electrolysis cell stuff better. So a fuel cell just produces electricity with hydrogen, say. You make the electrons, the hydrogen, the electrons and the protons combine to make the power. And the opposite of that is a water electrolyzer, where we put in power and we split water and we make the hydrogen. So fuel cells, electrolyzers are sort of opposite sides. Microbial electrolysis cells are somewhat in the middle because they're both positive, energy positive and overall energy negative. So in a microbial fuel cell, we don't have hydrogen, we have some sort of fuel that the bacteria break down. They release protons, goes over to the electrode, this becomes alkaline, releases hydroxide ions, and we balance charge in the chamber. And this work done by this guy Pascal, Cycli, and Gab at Kaust. Oh yeah, these guys. They put together this beautiful picture showing how the bacteria that can make electricity span all three domains of life: eukarya, archaea, and bacteria. And so there are an abundance of microbes that can do this. Although when you really get down and dig into which ones do this the best, so far, Geobacter sulfur-reducens has usually emerged as the dominant microbe in these reactors. Of course, that's not always true, and that's a whole nother talk for another day, but quite often it's Geobacter. So you take Geobacter, breaking down the organic matter, we convert that fuel into electricity, we take away the oxygen, and now nothing happens because it's thermodynamically unfavorable. But if we add a little bit of voltage into the circuit, then we drive hydrogen. And the key here is that we don't need to go to 1.5 volts that we need to do for water electrolyzers. We only need, in theory, about 1/10 of a volt to make this occur, because this is favorable, contributing about 0.3 volts. This is 0.414, so we only need to make up the 0.11 volts. Now, what we've learned from microbial fuel cells is how to start with laboratory systems and get all the way up to these big systems. So we've learned how to scale up the system, what makes it increase in power, what makes it increase in volumetric performance. And for those few researchers here, I'll go through this really quickly. On these large scale systems, we can mass manufacture these brush electrodes. There's whole modules of brushes. We combine each one of those brush ones with 2 cathodes. We link that so that we get 1 anode and 2 cathodes. We get about twice the power that we get from just having a single anode with a single cathode. And this is a polarization using actual wastewater at a large scale of about 1,000 liters. And we put this into a pilot scale operation, and what we found out was when you have a COVID emergency and everybody on this military base goes home and nobody's there on the weekends, that your power production pretty much follows the day, but really collapses on the weekends. But we at least got data during COVID when the base was partially shut down, which is good. But this is the data we got. This is going across all these individual modules. So we've got a total of 32 here, and you can see this is the power in each of those modules. Doesn't display any obvious trend other than it's sort of the resistance of each of the modules. After we had operated this for about 6 months, this power level had dropped and even failed in a couple of the modules. And that failure was due to leaking of water through these cathodes and also fouling of the cathode. The good thing about microbial electrolysis cells is we're not going to have this need for the oxygen reduction reaction at the cathode. We're going to have hydrogen evolution. And the COD removal is about 50%, which is pretty much what we expected. With the biofilter that we had attached as a secondary process, we got about 90% total COD removal. So this brings us to how we make use of this to improve the system and to scale up the MEC. And published this paper back in 2004. This is great. It's like one of my most highly cited papers. I convinced everybody never put a proton exchange membrane right against the cathode. It's a bad idea, and that hasn't changed. It's a bad idea for the reason we thought, one reason is that, you know, when you put that PEM right here, we thought that hot pressing it against this cathode sort of inhibited the performance of the cathode. Turns out that wasn't true. What the real problem was is we envisioned that that current was being supported by a proton transfer through a proton exchange membrane, when in fact, it is not being supported by that. At neutral to alkaline pHs, so at neutral to alkaline pHs, this reaction is dominated by hydroxide ions being released from the cathode. So what we really need here is an anion exchange membrane, not a cation exchange membrane. So the real problem was we were facilitating the wrong ion moving relative to the cathode. So what we did is we set up this architecture and we increased now the power from about 1 or 2 watts per square meter to 8 watts per square meter. So we're facilitating only hydroxide ion transport between now humidified air to keep this moist and not dry it out. We have a very thin liquid electrolyte. We're actually flowing it through the electrode. And because of the AEM, we're not getting any sodium or potassium transport into there. And because we have no electrolyte over here, we're not getting any phosphate or other buffer molecules to that electrode. So we use this very thin system. This is a felt anode. Water actually moves right up through the felt. And then a little spacers here to get some airflow through here. And with that, this is our power curve, and you can see way up here, right about 8 or 9 watts per square meter. If we use a non-platinum catalyst, and surprisingly here, if we use a platinum catalyst, it actually is worse. That's due to more to platinum inactivation than anything else. And if we use wastewater now, which has a lower buffer capacity and a lower conductivity, in a similar setup, but one where we leave some space for the wastewater to flow through there, otherwise we felt it might jam up this anode. This drops down to about 1 watt per cubic meter. 1 watt per square meter, that should be a 2. Just showing the impact of this pH change and conductivity change for almost the exact same system. So the good news is we figured out we could get 8 or 9 watts per square meter. The bad news is that for the actual wastewater, that wouldn't work so well. So we're going to have to take that information going into the future in MECs. But if you look at where we were back in 2009, we had pretty much plateaued here. Maybe plateaued's not the right word, but we were starting to reach these power densities. But now in the past few years, we've essentially jumped up. We've vaulted over where we were to increase this several times because we now understand the system better. And that's really what we want to do with MECs now, because we started off with these simple little chambers and got bigger and bigger. And what we eventually got really good at was making methane instead of making hydrogen, because all the hydrogen was gobbled up by the methanogens and they just made methane. And so we had to go back to a 2-chamber MEC and figure out how we were going to capture that hydrogen before it was changed to methane. And we had to use 2 chambers and ion exchange membranes. And by now flowing the liquid across these brushes, we were getting about 1 liter per day and about an amp or 2 per square meter, or 60 amps per cubic meter here. We then started to push the flow through these brush electrodes and to thereby decrease the volume, but also decrease the electrical resistances. And that went up by about 300 or 400%, now to about 4 liters per day, and current densities of about 5 amps per square meter. And we said, well, you know, we've just figured out how to make all this power in a microbial fuel cell. What if we use the same sort of idea in engineering and apply that to a microbial electrolysis cell? And we've done that. And now we're at 40 amps per square meter. Actually, we're up to about 50 now. And about 60 liters per liter per day versus about 4 liters per liter per day. So by making use of what we learned about the controlling resistances in the MFCs and how to scale those systems up, we've learned a lot more about how we can scale up MECs. But unfortunately, it means it's going to be still a challenge with wastewater unless we can control the buffer concentrations in that wastewater. And I think we can do that. We may have to add in things and then remove them later on, or maybe we have a cellulose system which is more self-contained. But at least we know how we can get there if we can get the right conditions to make it all work. This is just showing I said we were getting up around 50 amps per square meter. You can see that here. The phosphate buffer concentration really doesn't change anything in this system. We're not quite sure why, but we're going to try and figure that out. And the acetate concentration too didn't make a big difference. The intrinsic conductivity also doesn't. But if we had, if you think back to a PEM water electrolyzer, in a PEM water electrolyzer, they're using completely deionized water. There is zero conductivity in that system. So intrinsically, if we can not kill the microbes by going to zero conductivity, but we shouldn't need to have to worry about the pH the salinity and conductivity issues here. With the catalysts, we don't have to worry about the anode anymore because we have bacteria on the anode, so we don't need platinum on the anode like a water electrolyzer does. And we can use alternative cathode catalysts. The current densities that we're operating at, nickel and some nickel phosphide and nickel particles seem to work okay, but I think there's room for improvement there as well. And finally, let me end up talking about this 1-1-1 dream. So if we use water electrolyzers, we've got to do two things. We've got to purify the water. That's the first step. Whether it's, and Noureddin maybe will tell us whether he thinks that we should worry about the water purity or not. I know he's authored a paper on this subject, so I'm sure I'll have something to say there. But it's still a process. It's something we need to do. And then we have this electrolyzer operation. Now, the electricity use, just looking at the electrolyzer, this is thermodynamics. You need a certain number of electrons to make that hydrogen. And electricity is a certain number of electrons. So you need 33 kilowatt hours to make a kilogram of hydrogen, depending on whether it's heat or electrical power. That means that if you want to sell this if you want to have it worth $1, not sell it for $1, but cost $1, electricity needs to cost about 3 cents a kilowatt hour. That's thermodynamically 100% energy recovery, which you'll never do. So about half that with some reasonable efficiencies. So I don't think this is practical because electricity is never going to be that cheap. Somebody's going to buy it. I mean, at certain times of the day, it could be that cheap, but somebody's going to buy it if it gets down that low, if they can consistently get it. With biomass, well, it's not a perfect world, but at least we can say that, you know, this $1 a kilogram relative to electricity, because we need a lot less electricity because we're getting a lot of our electrons from the substrate and we're just augmenting the voltage of the circuit. It can be much more expensive. So electricity is not as critical for microbial electrolysis cells. What is the issue? Well, it's mostly getting the biomass to the reactor and getting the bacteria to break it down, which is a slow process. So we still have challenges in terms of handling the biomass and growing the bacteria and getting it to function in the system. So with that, you know, I want to say we can use bacteria as a catalyst to either promote electricity generation somewhat, but maybe more useful as microbial electrolysis cells due to the value of hydrogen being so much greater than that of the electricity. And if we can also treat wastewaters and get rid of that, that's a big advantage. I'd like to acknowledge funding. My current funding on water electrolyzers is from NSF, a long-time collaboration with NREL. I have a new project on DOE, and the Water Desalination and Reuse Center for many years of support for this work on MFCs and MECs. In particular on the MECs, I also want to acknowledge Ruggero Rossi, who's really been leading this work on both the MFC power advances as well as the water electrolyzers, Kyung-Yo Kim, and I already mentioned Lashi. And I think that is it. Yes, I'd be happy to finish there. Thank you. Answer questions if we have any.
So questions? No.
couldn't have promoted the question any better, I think, than.
Hello.
They have, yeah, it works. Thank you very much for this very insightful presentation. So a question on, or feedback on the water electrolysis and very brilliant idea to use RO membrane. But as I see it in the system, it's more doing FO, forward osmosis function than RO. So, and you cited many times FO. So did you try forward osmosis? Because it's quite different than RO, especially for the RSF, reversal flux and these things.
Yeah, I mean, that's a really good point, and we sort of know that, but getting FO membranes was a little tricky. In fact, the BW and SW membranes we got were from you guys. And we had trouble getting an FO membrane, but we now have one, and we are trying it out with FO membranes. But the biggest difference between the FO and RO membranes is that support structure, right? You just don't need it with an RO membrane. So we think in terms of doing FO, it'll probably be pretty similar because we don't think that structural support is doing a whole lot in our system relative to proton gradients driven across there. And let me emphasize that you know, when you're driving that current, you have to have those protons building up a big gradient there because that's going to drive their flow through there, just like, you know, reverse solute transport in a regular system drives ions the wrong way. But that's what really helps us, and that was sort of unexpected. So the properties of the active layer relative to enabling that gradient and then passing those protons through is relatively unstudied. Nobody's really looked at that. And so it's a very fundamental question of, you know, how well does that work? Because nobody ever looked. Nobody would care. I mean, if you're doing RO, you don't care about proton ion transport in particular. You got so much water flux through there. It's irrelevant.
Okay, so before you go, you can take with you a few, we can give you a few FO membranes.
Okay.
But my point is for the reverse salt flux.
Yes.
Because you have ions on the other side.
And so, right, to draw that water in, and as you know, because if you have a matched concentration, you know, if we keep that perchlorate at about the same concentration of seawater, we can match that, and then there's no draw. All you have to do is up the pressure a little bit on the catholyte to push it in. So that really would be more, you know, RO than FO. If we said, well, you know, if we can set the concentration and the anode side to be very salty, we never need to worry about it. It'll just happen. It does tend to slow down the ion flux against the water flux. So that's a consideration. So it might be that, you know, you for like an hour a day, you just switch and run water through there, refill it, and then electrolyze the rest of the day, that sort of thing. Yeah, I think for people to hear you online, you should need to use the mic. Oh, okay.
Hello.
Yes.
Hi,
hello.
Bruce. Thank you for an interesting talk. This is Hari here. And I really enjoyed the presentation. It was very informative to see the quantification of the energy that we can derive from the renewable sources. My question is how we can address the methane issues, as we know that the methane production is, as we can get from the anaerobic technologies as well as the landfills from the sludge. What are the best possible solutions to address this methane?
I'm sorry, could you clarify that? What's the best solution to address?
The methane production.
Methane.
Yeah.
So how do we best produce methane? Or how do we
how we can convert this methane? For example, for electricity, for current production, or maybe methane oxidation to some other compounds. What are the most sustainable ways we can address these methane issues?
Well, I mean, there's nothing inherently wrong. I mean, biogenic methane, if it gets converted to CO2, is not a net greenhouse gas. Because if you grow a plant, you make food, the food is eaten, it goes to the waste treatment plant, it comes back out. It's a zero methane emission scenario, zero CO2 emission scenario. If you leak any part of that methane to the environment, then it's a net greenhouse gas. So while we're capturing all that methane, it's just really, really important not to lose any of it in the wastewater or through leaks and so forth. I'm not sure I'm really answering that. Can you clarify? Did I miss anything?
So maybe a follow-up
Yeah,
question.
sure, good.
So you gave an example of a single chamber microbial electrolysis cell with high strength wastewater where you produce methane.
Yeah.
Then you decided to have a double chamber system to produce more hydrogen. So economically, which is better, to produce methane, or should we go with the double chamber to produce more hydrogen?
Yeah, methane's really cheap. So to try and sell that methane or use it you're never going to, I don't think it's worth putting the electrical power in there to make that methane ultimately to make methane. And that's different than if you want to drive the efficiency of the process to be greater. And that's what I think a lot of people are doing. They're not trying to make more methane so much as they are trying to increase the performance of making methane more. And I think that's where the electrolysis cells could help. But hydrogen is a valuable gas. Methane, not so much. So I think ultimately, if you can get hydrogen, it's a far better product economically.
Hey, Bruce, very nice talk.
Thanks.
Actually, I have one question regarding the water electrolyzer. You are using the R membrane for the separation and for the ion exchange. But my question is, if you use the salt water, does it have any effect on the catalyst durability? The lifetime of catalyst.
In the anode or cathode?
Both, I think.
Yeah. So catalyst durability is a huge challenge in any scenario. But let's assume that in the anode, it's a perchlorate solution, and you have very little ions leaking into that, and therefore it should be quite stable. On the cathode, that's a bigger challenge because you can get a highly alkaline local environment. With seawater, you could get precipitation of salts, which could affect stability of the cathode. So in that case, I think that's still a challenge. I think using probably the second process using brackish water might be more feasible, but in terms of the catalysis at the cathode, I hope maybe KAUST could solve that for me, because it would be great if the catalysis center could figure that out. That would be great. But that's not something I do.
They'll have 5 minutes.
Oh, it's okay. The clock's a little fast, but that's all right. One of the things about even in my own group, the researchers that do water electrolyzers don't necessarily talk to the people that do the microbial stuff. And so you really, pulling these communities into the same room is a little tricky sometimes. So I'm sure there's a lot of landscape here joined by electrochemical engineering or electrochemistry, but yeah, it can be a little overwhelming. Nordine.
Great perspective for future. What's the future for hydrogen?
Oh, yeah. Okay, so what's the future for hydrogen? And And the answer is, we really don't have an alternative. I don't think batteries can ever do all the things we need them to do. And you could say, well, they're going to invent a better battery. Yeah, maybe. But they got a long way to go if they're going to get close to the energy density of a tank of hydrogen. So I think hydrogen's going to have a big role in energy storage. The sun shines during the day, you electrolyze water. It gets really sunny at certain times during the day. You electrolyze water. The sun goes away, back through a fuel cell, or hydrogen into a gas turbine. Hydrogen can be both a method of energy storage and a transportable fuel. There's nothing else, I think, comparable to that in terms of what we need versus what we have, except fossil fuels, which are superbly superior in every which way than climate change. So, you know, I think water electrolyzers are absolutely going to be a huge growth industry. There's just no question about it. We use already far too much hydrogen. It's all made with fossil fuels. So just to turn that industry alone green is going to require massive amounts of water electrolyzers. For the biomass part, I don't see it as a big part of the hydrogen solution. I see it as a niche solution. I see it as, you know, for treatment plants or for cellulose or ag refineries or, you know, places you know, where you have concentrated organic streams that might be amenable. Could be a really great compromise in terms of energy product. But I think hydrogen is here to stay now. It's the vision for it is much different today than it was before. And I also could have shown you pictures of airplanes flying, being fueled by hydrogen. And from what I've seen, I don't think that's as likely. Just because of handling of the hydrogen, you'd have to have liquid hydrogen. And I think we're going to use fossil fuels and we're not going to make our goals in climate change. That's going to be one of the toughest things to do. And that's probably not going to be one we can address other than by liquid biofuels. So is that a big enough vision? Does that, you know, it's really, you know, I like to say I'm really good at predicting the future. And when I started doing microbial fuel cells, they said, how long before this is commercialized and we'll be running plants with microbial fuel cells? I said, 10 years. I said that like 15, 18 years ago. So obviously I'm not so good at predicting the future. But I just don't see where we have an alternative in this case. So we'll see what happens.
10 years ago, what comes? Let's say comes. We were talking about hydrogen, carbon, hydrogen or battery. Now we see more battery or hybrid than hydrogen.
The reason you see more batteries is twofold. One, the technologies really did improve. But two, we have an electrical infrastructure which is quite amenable to the battery infrastructure. And even now, people get battery anxiety or charging station anxiety to recharge their cars. The hydrogen part is going to be much more difficult. But we're seeing it for large transportation where there are railways or interstate highways or main travel routes to move big things. And so I think it's easier to do that for big transportation than it is for everybody's vehicle and putting hydrogen charging stations in your home and everything else. That I don't think that was really well thought out for anything but the most population dense area. So, as long as they don't crash. Yeah. Yeah, but the Hindenburg failed more because of the aluminum in that atmosphere, you know. Well, you take a big balloon and you put hydrogen in it, yeah, that's a problem. These are containers that have 700 atmospheres of hydrogen, and they can hold that quite safely. I don't know that, I think it would be hard to argue that a tank of gasoline is inherently safer than a hydrogen tank, or even a compressed natural gas tank. If it gets in an accident, there's going to be a problem. But under the normal conditions, it's quite safe. And hydrogen, when it's dense, also vents straight up. I mean, it's so light, and if it does also combust, it combusts straight up. I mean, you can get much closer to a hydrogen fire. Yeah. I think they're graphite wound metal tanks, but I really don't know. Yeah, that's not my area. I got enough to worry about. But it's worth, yeah, it's worth looking at. I don't know. It goes through metal, but it's embrittling metal that's more important. So I don't want to run over my time here. I think I'm over my time.
So let's thank our speaker one more time, please. Thank you.